Okay, imagine this. You're running a top-tier manufacturing facility. You've just invested millions in a brand new, sophisticated five-axis gantry machining center. It's, the centerpiece of your whole operation.
The pride of the shop floor.
Exactly. It's cutting these hypercritical components, maybe for aerospace or defense. Everything in the digital model is perfect, the code is flawless, but then the parts start coming off the line.
And they're failing inspection.
Right. They're just slightly out of tolerance, sometimes by only a few microns, but it's enough. They're scrap. And production just grinds to a halt.
And in that moment, that crisis moment, almost everyone, the operator, the manager, they immediately point fingers at the tooling or maybe the CAD programming.
Something simple.
Something simple, yeah. But the truth is, if your machine is suddenly producing scrap after months of success, the real villain is almost always the slow, gradual loss of its core integrity, its geometric accuracy.
And that is the high-stakes mission for this deep dive. We're going to get under the hood, past the software, and into the hard physics of what makes these machines precise. We want to understand why a machine this complex loses its geometry.
And then, crucially, break down the extremely rigorous process needed to get it back to factory spec. We're talking about using instruments that measure errors smaller than a bacterium.
And then physically adjusting these massive iron structures by microscopic amounts. The goal for you listening is to see that true precision, it isn't just about good code, it's about perfect physical alignment.
And we're going to explore that entire process, from finding the errors to fixing them using tools like laser interferometers and specialized ballbars.
Okay, let's unpack this. Let's start with the basics. Why does this physical geometry matter so much in the first place?
Well, geometric accuracy is it's the machine's most fundamental ability. It's about holding perfect, unchanging relationships between all its moving parts.
So if you tell it to move 100 millimeters,
It not only has to move exactly 100 millimeters, but that movement must stay perfectly parallel to its rails and perfectly perpendicular to the other axes. If it can't hold those relationships, you simply can't make complex parts reliably.
and what happens if you just, I don't know, live with the small errors? Maybe there's a tiny vibration or the surface finish isn't quite what it used to be.
That's a recipe for disaster. A truly catastrophic failure down the line. When you ignore those small errors, you're forcing the machine to fight itself.
What do you mean fight itself?
The motors have to work harder, the rails start to wear unevenly, things heat up. That small error, over time, it just multiplies. So you're not just scrapping parts today, you're actually accelerating the destruction of your machine for tomorrow.
So it's not just about making a bad part, like an oval instead of a circle. It's about long-term damage.
Exactly. You're killing the machine.
So what are the core elements we need to watch out for? You mentioned 4 of them.
Right, there are 4 pillars. The first is parallelism. Think of the 2 long rails the gantry runs on. They have to run perfectly alongside each other. If they diverge even a tiny bit, the whole system starts to bind.
And that leads to uneven wear, extra stress on the motors.
Precisely. And that brings us to the second pillar, which is just as critical, perpendicularity.
So making sure everything is at a perfect 90-degree angle.
A perfect 90-degree angle.
Yeah.
If your x-axis is off by, say, even 89.99 degrees to your y-axis, any square you try to cut will come out as a rhombus. And for 5-axis work, that tiny error just ruins the smooth blending between surfaces.
Okay, so that's the shape. Then there's positioning accuracy. The machine has to know where it is and where it's going.
Correct. When the controller says move 500 millimeters, the physical move must be exactly 500 millimeters.
Yeah.
No more, no less. This is the dimensional backbone. If it's off, your part's dimensions are wrong. Period.
And finally, the one that really proves the machine is stable. Repeatability.
This one sounds simple, but it's the hardest to maintain. It means the machine has to hit that exact 500 millimeter spot 1,000 times in a row without deviation. That's what ensures consistency from the first part to the last.
What's so interesting is that these errors, they don't just appear out of thin air. They come from real physical sources. So what are the main enemies we're up against?
There are 3 big ones, and they're all rooted in physics. Enemy number 1 is thermal deformation.
Heat.
Heat. We tend to forget that these massive machines are basically giant blocks of metal, and metal is very sensitive to temperature.
But how sensitive are we talking? Does the room getting a little warmer really affect a 50-ton machine?
Oh, absolutely. Think about the friction from the ball screws, the heat from the motors. Over a long shift, things warm up. A temperature rise of just 5 degrees Celsius can cause a 3-meter gantry rail to expand enough to shift the tool point by tens of microns.
So the machine is literally a different size at the end of the day than it was in the morning.
Exactly. It's bigger. And that throws off your positioning accuracy completely.
That's incredible. Okay, so that's heat. What's enemy number 2? You called it stress relaxation.
This one is slower, more insidious. The gantry is constantly supporting heavy loads, accelerating and decelerating them. Over years, that constant stress causes the internal structure of the metal castings to relax, to creep.
So the metal itself is slowly bending out of shape over time.
Precisely. It's like a very slow, invisible twist. And this is the main reason you lose parallelism, as those long rails subtly shift out of true alignment over years of work.
And the last one is the most obvious one, I suppose. Enemy number 3, mechanical wear.
Wear is just unavoidable. Every single movement creates friction. The guide rails, the ball screws, they just wear down. And that creates a tiny mechanical gap. Operators call it slop or backlash.
Like having a little bit of play in your car's steering wheel.
That's a perfect analogy. And that backlash completely destroys your repeatability. The machine can't land in the exact same spot twice because the physical connection between the motor and the tool is just loose.
So it's clear the problem is complex, which means the solution can't just be guesswork. You can't just walk up and say, I think that bolt is loose. You mentioned a very strict sequence for this.
You must never, ever attempt a physical adjustment before you have a complete map of all the errors. The sequence is always inspection and analysis first, then mechanical geometry correction, and only then do you do positioning and spindle tuning.
So step 1, inspection. What are we using to get this error map?
We're using instruments from the absolute edge of metrology. The main one is the laser interferometer. This isn't a tape measure. It uses a laser beam to measure distance based on the wavelength of light itself.
Wait, hold on. How does measuring light waves tell you how far something moves?
Well, think of it this way. The speed of light is a constant. The instrument counts the interference patterns as a reflector moves away from the laser source. By counting those waves, we can measure the distance traveled with nanometer accuracy. We run it across the machine's entire travel path.
So it gives you a complete high-resolution diagnosis of every single error.
Every single one. And we also use a ballbar instrument. That's crucial for checking circular movements. If the machine is cutting ovals instead of circles, the ballbar plot will tell you instantly if your axes aren't perpendicular or if the servos are out of sync.
So once you have that data, that map of the flaws, you move to step 2, mechanical correction. How on earth do you physically adjust something that weighs 50 tons with microscopic precision?
It sounds a bit counterintuitive, but for something like parallelism, we follow the laser data to the exact spot on the rail that's out of alignment. Then we actually loosen the mounting bolts that hold that rail to the structure.
You're saying this high-tech process involves tapping the rail with a hammer.
It sounds crude, I know. But we are dealing with immense mass. We use controlled force, sometimes a specialized soft hammer, sometimes a hydraulic jack to shift the rail just a tiny bit, maybe 20 microns at a time.
And you're watching the laser the whole time.
Constantly. It's a real-time feedback loop. We shift, we measure, we check the laser, and we repeat over and over until the data shows that rail is perfectly straight. It's a process of highly precise brute force.
That's amazing. And what about getting the axes perfectly square for perpendicularity?
For that, we're usually adjusting the gantry support structure itself. We use things like massive granite squares or, more often now, a laser level system. If the X and Y axes are off, we physically adjust the support connections until that perfect 90-degree relationship is back.
So now the machine is physically straight and square. That brings us to step 3, positioning and spindle tuning. You're fixing the motion.
Right. And the biggest adjustment here is something called pitch error compensation. This deals directly with the positioning errors we measured with the laser. Remember when the screen said 100 millimeters, but the machine only moved 99.995?
Right. The mechanical movement itself was flawed.
Exactly. And you can't always fix that tiny flaw mechanically because ball screws aren't perfect. So instead, we teach the CNC controller about its own flaws. We generate a compensation table, a map, that tells the software, hey, at this specific point on the screw, you need to drive the motor just a little bit further to make up for the error.
So you're not changing the metal anymore. You're changing the software's map of the metal. You're using software to fix a predictable hardware error.
That is the perfect way to put it. This compensation table is the final layer of accuracy. After that's done, we move to the spindle alignment.
And why is that so important?
Because a tilted spindle will give you a terrible surface finish, especially in 5-axis work. We put a high-precision test bar in the spindle and sweep it across the table with dial indicators. If it's tilted, even by a few arc seconds. We have to physically shim the bearings or adjust the whole headstock until it's perfectly perpendicular to the table.
Which brings us to the targets. Because it looks straight is not good enough. Data is everything. We need to know the numbers we're aiming for, usually based on a standard like ISO 230-1. This is where it gets really mind-bending.
It has to be. For aerospace parts, there is zero room for error. So let's look at those targets. For parallelism, we're aiming for less than 0.01 millimeters of error per meter of travel.
So over a 3-meter gantry, the rails can't deviate by more than the thickness of a piece of paper. Why is that number so critical?
Because any more than that. And the motors are constantly fighting that misalignment. It causes overload, vibration, and it just kills the machine over time. Hitting that target is the difference between a smooth machine and one that shakes itself apart.
And for perpendicularity, you said it's even tighter. 5 microns?
Yes, 5 microns. That's 0.005 millimeters. For perspective, that's about 1/10 the thickness of human hair. This is probably the most critical target for 5-axis work. If you miss this, your complex curved surfaces just won't blend correctly.
And what about the final positioning accuracy after all the software compensation is done?
For a high-end machine, the target is a total system error of plus or minus 0.005 millimeters. This is what guarantees your parts are dimensionally perfect, that the hole you designed is exactly where it ends up in the real world.
And the final proof, repeatability.
For that, we demand the machine returns to the exact same spot within plus or minus 0.003 millimeters. Hitting that proves the whole system. The mechanics, the electronics, the servo loops is perfectly tight and responsive. It guarantees consistency across thousands of parts.
So we've covered the steps and the data, but you mentioned external factors. There's this huge hidden variable that can ruin all this perfect work, the environment itself.
Oh, absolutely. The biggest one is temperature. I remember a calibration job on this huge machine. We worked for 2 days to get it perfect. We hit every single target. The client was thrilled, and he opened this giant loading bay door to let a truck in, a door that was facing the hot afternoon sun. That blast of warm air changed the size of that massive machine by nearly 20 microns in under an hour. When we checked the laser again, all our work was invalid. The compensation tables were useless. We had to wait until the next morning and start over.
So the ideal situation is a climate-controlled workshop locked at 20 degrees Celsius. But what's the workaround if you don't have that?
You have to wait for the machine to thermally soak. That usually means technicians coming in at 4 or 5 in the morning before any lights or other machines are on, before people are even in the building. The entire structure has to be at a stable, known temperature before you can even begin to measure.
And what else in the environment can throw things off?
Humidity, believe it or not. Not for the metal, but for the laser beam. High humidity changes the refractive index of the air, which affects the laser's accuracy. We have to constantly input air pressure and humidity readings into the interferometer software to compensate.
And it goes without saying, your calibration is only as good as your tools.
Absolutely. The lasers, the ballbars, they all have to be calibrated themselves by certified labs. And when you set them up, they have to be on rock-solid foundation, so no floor vibrations can skew the data.
So after all this work, is this a one-time fix? Or is it an ongoing process?
It's maintenance. It is absolutely not a one-time fix. We recommend a full geometry check every 6 to 12 months or immediately after any kind of crash. Even a minor crash can permanently twist the frame.
And the easiest way to stay on top of it?
Keep a logbook, a detailed one. If you track the error data over time, you can see trends. You can see, hey, the x-axis perpendicularity is slowly getting worse each quarter. That lets you spot a failing bearing or a worn component before it fails catastrophically and causes days of unexpected downtime.
That brings us to the end of this deep dive. It's clear that geometric accuracy is the absolute foundation, the heart of a 5-axis machine, and that regular data-driven calibration following the strict sequence is what keeps production profitable and extends the life of a multi-million-dollar asset.
And if you connect this to the bigger picture, you see just how fragile manufactured perfection really is. It's a constant battle against temperature, against stress, against these invisible forces twisting massive structures. And that brings up a really interesting question. Considering how much things like heat and microscopic wear affect these systems, how many other seemingly stable, large-scale systems in our world, from skyscraper trusses to giant radio telescopes, are also secretly fighting a constant losing battle against infinitesimal mechanical drift?